Quantization made your 70 billion model fit in 40 gubby buys. Real win. But here's the wall. It can't break. It's still a 70 billion model. That's 70 billion multipliers for every token on a phone, in a browser, under a tight latency budget. Smaller weights isn't enough. You don't need smaller weights. You need fewer weights. Different problem, different answer. Train a brand new, smaller model, fewer layers, fewer parameters to copy what the big one does. The big model is the teacher. The small one is the student. This is knowledge distillation, and the clever part isn't the shrinking. It's how the student learns. Here's the insight. Show a good classifier a photo of a dog. It doesn't just say dog, it outputs a probability for every class. Dog 90%, wolf 8, cat 2, car basically 0. Look at what that's secretly telling you. A dog is a little like a wolf, barely like a cat, and nothing like a car. The ground truth label is just dog. Train the student on that one hot answer and you throw all that structure away. But those ratios are real knowledge about how the world is shaped. Jeffrey Hinton called it dark knowledge. Free supervision the student could never get from the bare word dog. So distillation trains the student to match the teacher's entire distribution, not just the winner. But there's a catch. A confident teacher's distribution is too sharp. 99% on the right answer drowns out the interesting ratios underneath. So we soften it with a temperature knob inside the softmax. At temperature 1, you get the normal spiky distribution. Crank it up and the probabilities flatten, lifting the tiny ones into view. And those lifted probabilities are exactly the doggismo like a wolf signal the student needs. Teacher and student share the same temperature in training. At inference, the student drops back to 1. Now the loss. The student trains against two targets at once. A soft loss matching the teacher's softened distribution and a hard loss, plain cross entropy on the true label. So it stays anchored even where the teacher is wrong. You blend them with a weight, usually leaning heavy on the soft term, around 90%, because the soft targets carry the richer signal. There are 3 flavors. Response-based, the classic, matches final outputs. Feature-based goes deeper, matching the teacher's intermediate activations too. DistilBERT uses a version of that. But sequence distillation built today's small language models. For a closed model, you don't have its logits, so instead you have it generate thousands of high-quality answers and fine-tune the student on that synthetic data. The teacher's soft knowledge gets baked into the text. Stanford's Alpaca was built this way. The tween 26 twist is reasoning trace distillation. Have a strong reasoning model emit its full chain of thought, then train the student on input, reasoning, answer triples. The student learns to reason, not just to answer. That's how compact, open models suddenly got strong math and code skills. But the catch is sharp. The student inherits the teacher's blind spots. So the crucial step is a judge filter that drops the wrong traces before training. And does it work? DistilBERT, 40% smaller, 60% faster, keeping 97% of its teacher score. Alpaca, instruction following from distilled examples for around $600. The headline to remember. A good distillation keeps roughly 95 to 97% of the teacher's quality at a fraction of the size if the student's big enough and the data is good. So how does this compare to quantization? They change different things. Quantization makes each weight cheaper to store. Distillation makes there be fewer weights to compute. Quantization saves memory and bandwidth. Distillation saves actual flops, the only thing that makes a model fundamentally faster per token. And here's the beautiful part. They compose. The strongest small models are distilled first, then quantized. Distill to cut flops, quantize to cut bytes. A 7 billion student in 94 ends up 40 times smaller than its teacher and genuinely faster, not just smaller.